Let's do some 3.8 homework. So first, number 2, they tell you that B is the number of bacteria and T is the time in minutes. So we know they also say, let me read the question. They also say that, let's see, they want us to find its relative growth rate. So I think the assumption is there that it's growing exponentially. Oh, yeah, they say it divides into 2 cells every 20 minutes. So that's nice, exponential growth. So that's going to be what our model looks like. And then they tell us that the initial population is 50 cells, and so that in 20 minutes it should double. So that means 20 minutes would be 1/3 of an hour. So when you plug in 1/3 of a time, you should get out 100 for your number of bacteria. So then when we solve, we get this. So now this is in exponential form. We can convert this into log form. And notice it's log base e of 2 is equal to r over 3, but log base e of 2 is just natural log of 2 is equal to r over 3. So we end up getting that 3 natural log of 2 is what r is. But hey, guess what? Since you have a number out in front of a log, you can bring it up as an exponent. And so this is really natural log of 2 to the 3rd. Or in other words, the natural log of 8 is what r is. So after t hours, if this is our function, where we now plug in natural log, 8 for our rate and 50 for our initial value, I can now find out another way to rewrite it. And another way to rewrite it is if you have something raised to a power where you're multiplying, you could break it up into raising it to the first power and then raising it to the second, because we know if we raise to a power and then raise again, we multiply, but we can also work backwards to write it like this. And why would we do that? Because e raised to the natural log of stuff just gives us that 8 back. So this is a very beautiful way to write that. So this is telling you that every hour this thing multiplies by 8, which makes sense. If every 20 minutes it doubles, every hour it's going to multiply by 8. So that's our function. So why does that help us? Yeah, is that it? So that's 2a and b. There you go. So then here in 4, we contain 100 cells, and it grows at a rate proportional to its size. Exponential is another way of saying grows at rate proportional to the size of the population, right? Remember, that was change is equal to some constant times the size of the population. We know that this is the answer to that sort of a question. So if that is our function, they say that after 2 hours, we should have 400. So after 2 hours, we should have 400. That gives us this. And then after 6 hours, we should get 25,600. That gives us this. Well, notice we can solve both of these for B naught and then set them equal to each other to get this. Cross multiply to get this. And then divide both sides by 2k and 400 to get this. And so now here's an equation that we can solve. We'll notice that this is in exponential form. We can just convert that into log form. And so we notice that 64 is the same as 2 to the 6th. Then we can end up pulling that 6 out front as a constant. Then if you divide both sides by 4, you get this, that your k is equal to 3/2 of a natural log of 2. So in other words, k is approximately this value. So that means about 104% every hour is our relative growth rate. Okay, so then when we look at B, if this is our equation, I can plug in for time a 2 and plug in for K what we found, because they said that after 2, it says what was the initial size of the culture? We know that after 2 hours we get 400, so I plug in 2 and 400, and that allows me to solve for B naught. These cancel out and give me this. Then I realize that this here is almost in exponential form. No, we just divide so that we can solve for that B naught. So we get this. But then we can end up taking that 3 and pull it up here. So I have 2 to the third. But notice that that's just 8. So if you have e raised to the natural log of 8, they cancel out and just give us 8. So B is equal to 50 bacteria. Here, if this is our function, we can plug in the rate that we know and the initial value. But realize what happens. If we have e raised to the this times this, I could break it up into raising it to this and then raising it to this. And the reason I would do that is because these cancel out in a sense. So you get 2 to the 1.5t, and that is our function. And that's what part C is. Then for part D, it says what happens after about 4.5 hours, we end up getting this many bacteria. And so then it wants to know, find the rate of growth after 4.5 hours. Well, the rate of growth is just the derivative. So I end up getting this for my derivative. And then I plug in 4.5 to get a derivative, which is in terms of bacteria per hour. Then it wants to know when do we get out 50,000. I just set it equal to 50,000 and solve using precalculus. Yeah. So if this number is equal to this number, one thing you can do is you can take the natural log of both sides, and that allows us to then take this exponent. I can then take this exponent and pull it up front, and then I can divide by this times this, so I get about 6.6 hours. Okay. 8, if this is the amount of strontium in milligrams and T is time in days, they tell me for number 8 that it has a half-life. And this is the half-life formula. It's just an exponential decay type formula. So if this is my formula, well, if the half-life is 28 days, that means the amount that we get out is initial divided by 2 when T is 28. So initial divided by 2 happens after 28 days. So then I can divide both sides by A naught to get this. And then take it from exponential form into log form. I think you very quickly see that you get this. But then notice the natural log of a half is equal to the natural log of 1 divided by the natural log of 2. But the natural log of 1 is 0. So this is just equal to that. And it makes it look much nicer. So that's my K. So that is now my function. So then it wants to know what happens after 40 days. Well, when you plug in 40 right here, you end up getting about 18.6 milligrams left over. And then it says how long until it's equal to 2 milligrams left. You can just end up plugging in 2 here. So now you get it in exponential form. This is exponential form. And I can end up putting it into log form. So in log form, it's this. So it's just a number times t equals this. You divide, and you get that t is approximately 130 days. D as in donut, there's what the graph looks like. It's an exponential decay, but at 0, we get this starting value. Okay. Newton's law of cooling. The reason why these can be interesting is, here's what Newton's law of cooling says. Let's look at that first. So what it tells you is that the change in temperature with respect to time of a object, for example, let's say we had a hot cup of coffee and its temperature its change in temperature is going to be proportional to the difference between its temperature right now and the temperature of the surrounding medium. So for example, if this is a really big temperature minus the surrounding medium, so maybe I have a big difference. I'm like much hotter than surrounding medium, like a super hot cup of coffee compared to the air temperature around it. Then that means my change in temperature will be really, really big, yes? So we'll be changing temperature very, very quickly, okay? All right. But the way to make this work, this is really the key move, is this is our key move right here, that you let y equal to this difference between your temperature and the surrounding medium. That's really, this is key. We're going to use a change of variables. That's super, super helpful. The change of variables is going to be super, super helpful. So now every time you see this, you just replace it with a y. So all this can become y, which is much easier. But then if you take the derivative with respect to time of both sides, the surrounding medium we are assuming is constant. And so the derivative of this just tells you that y prime is equal to t prime. So t prime is y prime, all of this is y, and k just stays k. And so now there's a differential equation we know the answer to. The answer to that one is this. So this is going to be our model. Every time you have to remember, though, make sure you remember y is difference between stuff and surrounding medium. Surrounding medium. That's really a big thing to remember. Y is just the difference. So y is a difference between the surrounding medium and your stuff. Okay? So that means if we want to know why not, that's the initial difference between the 20 degrees in the room and the 32.5 degree Celsius cup of coffee. So we start off with that much of a difference. So this is our equation. Here at time 1, they say your cup of coffee is this much, but the room temperature, again, we're assuming it's fixed, is that. So that means y at 1 is 10.3. That's the difference. So after 1 minute, we get 10.3. Hey, yes.
Are you busy?
I'm making a video real quick. What's up?
Oh, never mind.
You sure?
Yeah, I was just going to ask you, are you giving a final on Thursday during second block or a test?
Am I giving it during which? This Thursday?
Yes.
No.
Okay, never mind then.
Okay.
I just have a kid that I have to be gone in the morning.
Yeah.
I need to send a kid somewhere to take a test.
If they need to just sit outside, they can.
Is that okay?
I can watch them. Absolutely.
Okay, perfect. I just thought if you're testing me, he could just easily go in there. But
Yeah.
if you don't mind him.
I can watch them. I'd love to. No big deal.
Okay.
Yep. I mean, I wouldn't love to, but I'd be more than happy to help. So thank you guys for waiting for that. Nice colleague. So we've got k is equal to this. And so what does that mean? That means in our equation, this is what k equals. This was our initial value. Then they said, what is this? Oh, we're not talking about cups of coffee. Sorry, we're talking about a dead body. Yeah, this is kind of gross. So the body was 37 degrees. They want to know if the body started off at 37 degrees, how long ago was that? So 37 degrees means that it must have been a difference in temperature of 17. So how far back was the difference in temperature 17? Well, you end up getting negative 0.1588 hours. That means the person died about 1.5 hours ago. Okay. So again, just to recap, the way you use these Newton's law of cooling ideas is that it's your temperature, the rate of change of your temperature, is the difference between you and the surrounding medium, which we're assuming is constant. So when you let this just be y, that means that dt turns out to be y prime. So then I can change a conversation about your temperature to a conversation about the difference between you and the surrounding medium. So that's what we're really modeling, is the difference between you and the surrounding medium is your original difference, e to the kt. Yeah? And so surrounding medium, in this case, again, it was dead body. So the dead body starts off at 32.5 and the room is 20. Then the initial difference is this. We did a bunch of work, and then at the very end, they wanted to know, okay, you've got your swanky model here where it's your temperature difference is this. Well, I want to find out how long ago was the difference between you, the person, and the medium 17, because we assume that the person started off at 37 degrees Celsius before they died. So the difference is 17, and we solved. Great work. Same sort of dealio, but now we have a cup of coffee. So it says that we're in a room of 20 degrees Celsius. Coffee cup is 95, so it's super hot. So the difference between those is 75. So our difference between the coffee and surrounding medium is equal to, starts off at 75 e to the kt. But they said that when the cup was 70, it was changing at a rate of -1 degree every minute. So what does that mean? That means the difference would have been 50. So in other words, y is 50 when the rate of change is -1. So notice, if we use this equation, we can now use it to solve for k. So that's what we're doing here. We are going to find k. Thus, this is true. So right here, we're now going to find t, because you're saying, okay, how long will it take to get to 50 for the difference between, how long will it take to get down to 50 degrees? Well, you're solving for t, and you're saying that the difference is 50. And when you do, you end up getting 20 minutes. Yes. Awesome. Have a great day, and I'll talk to you soon.